At first, happy Robindra Jayanti. Today, I will start one quarters about Rabindranath. The highest education is which does not merely gives us information but makes our life in harmony with existence. Think this quarter because this is very important quarters for our life. Just think. So happy Rabindra Jayanti again. Today's goal of this lecture, today I will say number of counting homeomorphism. In my previous video, I had seen how many homeomorphisms exist from a group to another group. But actually today's goal of this lecture, today I will see number of counting one onto homeomorphism from one group to another group. This is actually today's goal of this lecture, because in my previous video I had discussed briefly how many homeomorphisms exist from a group to one group. But at first I will hardly recommend you please see my previous video, my previous lecture, counting homeomorphism, how many counting homeomorphism exist from a one group to another group. Then today's video would be so easy. I have given the link how many homeomorphism exist from a group to another group in my description box. If you don't see my previous video, please see my description box. Okay? Let's see first example. First I will say, now I will see how many homeomorphism exist from a group Q8 to Zn. Shortcut trick. Number of homeomorphism from a group Q8 to Zn is 4 when n is even. And when n is odd, then this is equal to 1. This is actually, at first I will see, this is the shortcut trick, but I will see how 4. Why the number of homeomorphism from Q8 to Zn when n is even 4? Why 4? This is I will see. And when n is odd, why this is 1? This is I will also see. All of us know Q8 contains the element plus minus 1, plus minus I, plus minus j and plus minus k. And the normal subgroup of Q8 are H1 which is identity, H2 which is plus minus I, H3 which is contain the plus minus 1 and plus minus I, H4 contain plus minus 1 plus minus j, H5 contain the element plus minus 1 plus minus k, and H6 equal to Q8. This is the normal subgroup of Q8 we all of us know. Now Q8 modulo identity, this is actually would be isomorphic to Q8. Q8 modulo H1 which is contain plus minus, here plus minus 1. Plus minus 1 obviously member of ZG. So Q8 modulo H2, this is would be isomorphic to K4, because since this is the member of ZG, H to be the member of ZG, we all of us know that this theorem, G more ZG is isomorphic to a cyclic group, that imply this is the Q8, the group G is abelian. But here Q8, G means Q8 is non-abelian group. Q8 modulo H2 would be isomorphic to non-cyclic group, and we all of us know the in order for the non-cyclic group is K4. Similarly, Q8 modulo H3, this is would be isomorphic, since H3 contain plus minus 1 plus minus I, this would be, this is 4 element, this is isomorphic to group of order 2. We all of us know group of order 2 is Z2. Q8 modulo H4, this is also isomorphic to Z2. Similarly, Q8 modulo H5, this is also isomorphic to Z2. And Q8 modulo Q8, this is isomorphic to trivial group identity. So here the number of homeomorphism is, notice here Q8 not be subgroup of Z12. Similarly, K4 be not subgroup of Z12. Only subgroup is Z2 be the subgroup of Z12. Here also Z2, since this is subgroup of Z12, this is subgroup of Z12 and this is subgroup of Z12. So number of homeomorphism, automorphism of Z2 is always phi 2, this is equal to 1. Number of such Z2 type is 1, 2, 3. So this is 3. That means number of homeomorphism, this is 3 and this is trivial. That means 3 plus 1 equal to 4. That means I hope my all viewers have understood when n is even, then why Q8 to Zn number of homeomorphism is 4. If you consider similarly Q8 to Z12, Z10, then these would be also, number of homeomorphism would be also 4. I hope my all viewers have understood. When n is odd, then number of homeomorphism would be only trivial homomorphism. Then this is possible. I hope my all viewers have understood this is clearly. Okay? Oh well. Next I will say number of 1-1 homomorphism from Z5 to S5. This is the trick. Number of 1-1 homomorphism from Zm to any finite group, where G is any finite group, are number of elements of order m in G dash, where G is a finite group. Here the question, number of 1-1 homomorphism from Z5 to S5. That means we have to prove, we have to find element of order 5 in the group S5. And element of order 5 in S5 are such type of partition: 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 2 plus 3, 5. That means elements of order 5 are such type 5 factorial over 5 to the power 1 times 1 factorial, and this value would be 5 times 4 times 3 times 2 divided by 5, and this value would be 24. That means number of 1-1 homomorphism from Z5 to S5 is 25. This is the shortcut trick. Okay. Next I will see number of 1-1 homomorphism from Z5 to Q8. We have to find number of element of order 5 in Q8. We all of us know there exists no element of order 5 in Q8, and Q8 contain the element plus minus 1 plus minus I plus minus j plus minus k. If there exists a mapping f from Z5 to Q8, then if kernel is identity, then the mapping is 1, 1, we all of us know. And by fundamental theorem of algebra, Z5 divided by identity, this is actually would be isomorphic to Z5, and this is not be subgroup of Q8. So there exists no 1-1 homomorphism from Z5 to Q8. Next I will see number of 1-1 homomorphism from Z to Zm always does not exist. Why? If considered there exists a mapping f from Z to Zm, then kernel f would be, if there exists 1-1 homomorphism, when 1-1 homomorphism, when kernel f is contain identity, we all of us know. And fundamental theorem of algebra, Z modulo identity is isomorphic to Z, which does not subgroup of Zm. So there exists no 1-1 homomorphism from Z to Zm. Okay. We will see the number of 1-1 homomorphism from K4 to S4. The shortcut tricks is number of 1-1 homomorphism from K4 to Sn, When n equal to 4, then this value is 24, and when n not equal to 4, then this value is 6. When f be a mapping from K4 to S4, then number of 1-1 homeomorphism is kernel F is identity, and K4 modulo identity, this is isomorphic to K4, and we all of us know automorphism of K4 is actually S3, which is 6, and there exists subgroup of K4 type in S4, number of subgroup is 4, so this would be 24. Have you understood why 24? And when n not equal to 4, then this value would be 6. Okay? I hope my all viewers have understood why this is 6. If K4 to S5, then K4 modulo, here S5. Identity, this is isomorphic to K4, and this is obviously subgroup of S5, and automorphism of K4 is S3, this is equal to 6. In S5, there exists only one subgroup of K4 types. So this value would be 6 times 1, and this value would be 6. So there exists 6 homeomorphism from 1-1 homeomorphism from K4 to S5. Next I will see number of 1-1 homomorphism next from Z6 to Z12. We all of us know number of 1-1 homomorphism from Zm to Zn. This value is 0 when m does not divide n, and phi m when f divide n. Since here 6 divide 12, then this value would be phi 6, and we all of us know phi 6 means phi 2 times phi 3, and this value is 1 and this value is 2. So number of 1-1 homomorphism from Z6 to Z12, this value would be 2, and this is the actually shortcut trick. And this type of problem actually very important for any competitive exam. Okay? OL. Next example, G be the cyclic group of order 8, and A is equal to S5 be the permutation group of order 5. That means there exists homeomorphism F from Z8 to S5. Then which of the following statement are necessarily true? Option 1. There exists no non-trivial group homomorphism from G to S. Option 2. There exists no injective homomorphism from G to S. Option 3. There exists no surjective group homomorphism from G to S. And option 4. There exists more than 20 different homomorphism from G to S. For this, here the mapping cyclic group of order 8 is Z8 to S5. F from Z8 to S5. How many group homomorphism exist? Here the normal subgroup of Z8 are identity, Z2, Z4 and Z8. Z8 modulo identity. This is actually isomorphic to Z8, who is not be subgroup of S5. Z8 modulo Z2, this is isomorphic to Z4, and obviously this is subgroup of S4. And automorphism of Z4. Automorphism of Z4 equal to phi 4, and we all of us know phi 4 means 2. And how many subgroup of order Z4 type in S5? This is the partition such type 4 plus 1, and this is equal to 5 factorial 4 to the power 1 times 1 factorial. This would be 5 into 3 into 2. This value would be 30. That means number of subgroup of or 4 in S5 are 30 over 5/4, and these value would be 5/4 means 2. This is equal to 15. So there exists 15 subgroup of order 4 means Z4 type in S4. That means this value would be number of homeomorphism, automorphism of Z4 times 15. This value would be 45. Next, Z8 modulo Z8. This is actually trivial homeomorphism. That means there exists 46 group homeomorphism. So option 1, there exists no non-trivial group homeomorphism. This is wrong option. Option 2, there exists no injective group homeomorphism. This is right. Because when injective, then kernel would be identity. When kernel identity, then this is isomorphic to Z8, and Z8 not be subgroup of S5. So there exists no injective homomorphism. This is true. Option 3, there exists no surjective group homomorphism from G to S. Is it true? On-to group homomorphism exists from Z8 to S5? No. Because here the order of S5 is more than Z8. When onto homomorphism exists, then f of Z8 would be equal to S5. But here order is more than f of Z8. This order is the order of S5 is more than. So there exists no surjective group homomorphism from G to S. This is also right option. There exists more than 20 different group homomorphism from Z to S. Obviously this is right. That means option 2, option 3 and option 4 is the right option. Okay, I hope my all viewers have understood this question easily. Okay, well. Today I will stop here. In my next video, I will discuss another topic of group homomorphism. How many onto group homomorphism exist from one set to another set. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.